Hi, in this video we're going to go over the proof of existence and uniqueness of second-order linear equations again, but more of with functions and actual integrals and with less and operational algebra. So here's a statement. We still need existence and uniqueness for the first-order linear or nonlinear, just the first-order equations, and a and b are the functions, continuous on whatever the interval that we're in. It could be negative infinity to positive infinity. And the first part of the theorem is about the factorization of this second-order quadratic operator expression. Ax and bx are the coefficients, and it can be factored into linear followed by another linear operator. And qx in here is the solution of this nonlinear first-order differential equation because of the y squared is nonlinear. And px, once we have a qx in there, is a minus qx. So as a suggestion here, a solution is just a one differential equation with no initial conditions or anything. So qx can be replaced by all the different solutions, and then px is going to be different. So there's no unique way of factoring these quadratic operational expression into a product of two linear operators. So I moved a little bit so that I can show the second part of the statement. So once we have this one, we're going to look at actually the second-order linear differential equation, which is associated with this operator, linear operator. That's exactly this one. Right inside is the function in x. And with the initial condition, typical initial condition, function value and value of the first derivative, we want to show has one and only one solution. Of course, this will be broken down to, or is decomposed to, this two linear operator, and we're solving one at a time. That's how this proof of the second statement goes. So let's take a look at the first proof of the first statement. So here's the statement again. So first we have to think about this existence of qx. Qx is a solution of this one. Of course, there's the existence and uniqueness of first-order equation. This is a first-order differential equation, nonlinear, but it has a solution. You can put any initial condition, one y of a or equals 1 or 0, whatever number you put it in there, and there will be a solution. That's the existence and uniqueness theorem. And qx exists, therefore that's the solution, and px is under that statement is defined like this, a minus qx. So what we have to show is that with this px and with this solution qx, we show those two operators are equal to each other. So here I'm showing you again the operators are this. We just figured out, wrote down what this px and qx is, and we show if you actually expand this one, you get this quadratic operator there, where ax and bx are given. Because the way that quadratic, the product of those two linear first-order operators are expanded, it requires q prime x. So I'm writing down this what this q prime of x is this is the, and q prime here, q is a solution of this differential equation, so therefore q prime here is, if you isolate this y prime, you get y squared on the right hand side, which is this part, and negative ay with qx in it, and plus b. So since qx is a solution, we have this property of the q prime of x. So this is the lemma that was introduced in some other parts of my video. If you have px here and qx there, the way this product of two operator unfold is that the coefficient of d on the left here is the sum of these two coefficients, just like a quadratic polynomials. But the constant part, not the constant part, the coefficient of the identity part, is slightly different. We have the usual px times qx, but we have q prime x kicks in, which is the coefficient of I in the second factor there. Now, if you replace this px, which was set to be a minus qx, and here is a minus qx, and easily see that's just simply a here, so that recovers the coefficient of d part. And for that q prime x, we found this q prime x in a different version here using this differential equation. That q prime, that place is replaced by this q squared minus aq plus b. So that part there goes there, and we rewrite this px there with a minus qx, and everything is going to be in terms of q, a, and b. So here it is. Then you can see that q squared and negative q squared cancel, and positive aq with cancel with a negative aq leaves only b part in there. That's how things are set up. So that proves this the product of two first order operator becomes exactly the arbitrary one that we started with. So that's the proof of the end of the proof of the part 1.